Hello everyone. The second visualization of complex multiplication over complex or imaginary quadratic rings or fields, I think is largely due to a mathematician called Felix Klein. It's called a similarity transformation. You're going to see that the relationship between this and adding the angles and multiplying the moduluses, absolute values, or the magnitudes of the vectors we're going to be representing the complex numbers with. Anyway, we'll get going because we don't have very much time. What you do here is you start off by forming a triangle, one of whose sides is unity, that is, has a length of 1, uh, against the lower vector. You can see what I'm doing against one of the vectors here that we're going to be multiplying. Then what we're going to do is we're going to get the length of the second vector. Here, this one here, the 2, 6, or the second complex number, if you will. And we're going to dilate that triangle we just made, okay, using the dilation tool here in Cabri. Dilate this triangle using this factor, the magnitude of the second vector, around the origin. Okay. There is, I think, an easier way to do this in Cabri, just with doing the dilate function, everything I'm doing here, but I can't figure out how to do it, so I'm doing it in 2 steps. Then the next step is we're going to rotate this triangle, okay, about the origin through this angle here, which is the angle that is associated with the second vector or complex number. Next, we're just going to hide this triangle again to the bigger triangle here, just to avoid some confusion. Then if we follow this second triangle up here, and we'll find out the coordinates, it should be the product of those two complex numbers, -2, 3, 4. Again, I've worked it out to see if it works. 5 plus 2i times 2 plus 6i does in fact equal -2 plus 34i. So that definitely works out. Now, I was saying you're going to be able to see the relationship here. You notice these are both similar triangles. Okay. There are going to be, you're going to be dilating this smaller triangle by the magnitude of this side here. Okay. So that's going to make all the sides of the triangle proportional. Now what you're doing when you're dilating this side, when you dilate a triangle, you're going to be multiplying all the sides of the smaller triangle by this 6.32 here. That is the magnitude of the second vector. So this side here, which is the magnitude of the first vector, is being multiplied by the magnitude of the second vector. That gives you this side of the bigger triangle, which is the magnitude of the product. As far as the angle is concerned, is when you rotate it and such, what you're doing first, this triangle along this angle here near the origin has the angle of the first vector or complex number. And when you rotate it through this angle here of the larger vector, you're adding the 2 angles. So you see you're kind of accomplishing the same thing. Anyway, let's go on so I can demonstrate this works with the other quadratic fields. And again, I think this was z. This is going to be z of 2i. And let's just see, in fact, demonstrate that it does in fact work. And when we get on to division, you'll see that that works here too, as well as with the other method. When we get on to that too. Okay, we've got that triangle. We're going to dilate. Well, actually, we've got to take our length first. Sorry, we've got to take the length of the second complex number, the magnitude or absolute value or modulus, or the magnitude of the vector representing it. Then we have to dilate this first triangle here, okay, by this factor of the magnitude of the second vector or the modulus of the second complex number, right? And then what we have to do is we've got to rotate the bigger triangle, okay, around the origin, okay, through the angle of the second vector or complex number. And we're going to hide the first dilated triangle. And then we're going to go up here and we're going to see what point this is that it is pointing towards. Just set the very limit of Cabri, whatever. And oh right, we have to, since this isn't the fundamental lattice, since this isn't nearby, we could do that. Click on the axes, and it tells us that it's 3244, which it's 3244. Let's see which is what we got up here. 8 plus 2 times the square root of negative 2 times 6 plus 4 times the square root of negative 2 is indeed 32 plus 44, which is what we got up here. So yes, indeed, 8264. Yeah, so that does in fact work out. And then let's continue on to the last example. And figure 3. Okay, and this one, which is right, this one is the Einsteinian integers, the maximal quadratic integers of z of negative 3, if you will. So again, we need to form a triangle from here to this point to this point. Then we need to get the length, the magnitude, the absolute value or modulus of the complex number, if we think of it that way, and put it up there. Then we need to dilate this first triangle. Like I said, I think you can do this in one step in Cabri, just using dilation, but I haven't figured out how to do it yet. So, but doing it in 2 steps, actually, oh, I didn't finish that off. We got to dilate this triangle by this factor around the origin. Okay. Then we have to go to rotate this triangle around the origin through the angle of the seconds. What? I think I messed that up. We'll try again. Hold on. Rotate, not doing so well. This triangle around this point. Let's do it point of angle, vertex of angle, and final point. Boom. Okay. Then I'd just like to hide the first dilated ones because I think it kind of confuses things. And let's go over here and see if that points to find out the coordinates. Boom. Boom. And it says it's negative 516 is the product of those two. And indeed, 5 plus 3 rho, whatever, 2 times 2 plus 5 rho in the Einsteinian integers is indeed negative 5 plus 16p. So you see, indeed, it does work. As I said, you can kind of see what's happening in that, in fact, in a sense, it's doing something very similar to what the first visualization did. And that, you know, you're essentially just doing it with these triangles. So you're multiplying the magnitudes or the modulus for absolute values, and you're adding angles. Anyway, I think that's a very interesting one, and with both of these you can easily visualize division. The third one is a little tricky and needs an adjustment depending on which quadratic field or ring you're in. Anyway, we'll get to that in a moment, and we'll consider division separately because 10 minutes for each of these is long enough. Anyway, I got to end this. I'm sure it's coming up close to 10 minutes.